In the previous class, we discussed about something called Maxwell's equations, which discuss the relationship between electric and magnetic field or flux or displacement, whatever you may want to call, in any medium. So whether it is field or flux or displacement, then essentially the quantities are very similar, in the sense that even though some of these quantities are medium dependent, some are medium independent, we have proved that these quantities are essentially dependent on the field using a linear relationship. So now what Maxwell proved was that electric and magnetic fields in a medium are dependent on each other. So let's take an example and see this. We have already discussed this particular example. Suppose there is a small current element of length dl and the current is I. Then at some point away from this current element, if this distance is some r and the unit vector is r cap on this direction, we know that a small incremental magnetic field will exist. So we know that this dH is given as the cross product of the length element and the distance element. So this is as per the Biot-Savart law. So we had also proved that the nature of this magnetic field is such that it will enter the plane of the paper at this point. Now, although we have the Biot-Savart law, we have not said much about the nature of this current. Now, if this current is a constant, that is like saying it is DC, then even the magnetic field intensity will be constant, because there is no other quantity in this expression which is changing. So suppose because of this DC current element, there is a DC magnetic field also which exists, or a constant magnetic field. So in that case, the magnetic field will exist. But what will be the effect of the magnetic field? What will be the effect of this magnetic field? Can it generate any electric field? We know that using Ampere's law, the curl of the magnetic field is nothing but the sum of the conduction and displacement current densities. So if you assume that this point at which we are looking at is in space, or in some medium where the conductivity is 0, or let us say a perfect insulator like space. So if I write over here, so there can be no concept of a conduction current in space, because space is a perfect insulator. No charge carriers can exist. So therefore this quantity will go. Now at At this point there will be no J, but overall, since this magnetic field is enclosed around this current element, so in that case some J will definitely be there corresponding to this current. Now whether it's a closed loop or something like that, that comes later. But due to the static nature of this magnetic field, there may not be any electric displacement. So therefore, if there is no electric displacement, there will be no electric field. So definitely in space the current may be zero, but overall this magnetic field is enclosing this current element, so there will be some J corresponding to this current. But since the magnetic field is static in nature, there will be no electric field which is generated. So a simple conclusion is that if you want fields to coexist, they must be time varying in nature. One more example is that if you have a static charge. If you have a static charge somewhere in space, and without getting much into how that charge got there, suppose somehow it is there, then around the charge there will be some electric field. But since the charge is not changing and there is no other quantity which is changing, the electric field vector will also be constant in magnitude. Hence, only that electric field vector will exist. It will obey Gauss law, but it will not be able to generate a magnetic field, because as you know, the curl of E, which will give you the idea of the magnetic field variation with respect to time, that will essentially not exist because the E will be constant. So the bottom line is, if both electric and magnetic fields have to coexist, they must be time varying in nature. So now we will say that without getting much into what the nature of the charge and current are. So as you know, we know that both E and H fields are correlated because their cause is rather similar, and that is the charge. So static charge, as we know, causes electric field, where moving charges cause magnetic field. So Maxwell proved that since the cause of these are essentially the same, E and H fields are correlated. Now let us assume that we have the charges or currents, let's call this as current, either static charge or current, which are time varying in nature. And suppose they are kept at some point and we are observing a point which is far away from the charges that cause the field. Then in that case, we can definitely apply the Maxwell's equations and see in more detail what could be the solution for the Maxwell's equations and in what way the E field and H field coexist. So we expect that since Maxwell's equations are essentially interrelated by means of E field, H field, B and B or whatever, the charge density or the current densities, they must provide or converge to a solution which satisfies all the conditions for which these E and H fields must exist. So let us make our life little simple. Let us assume that we are in an unbounded, infinite, homogeneous medium. So what this means is that the medium under consideration will be infinite in size. There is no boundary. If you remember, we had discussed the boundary effects briefly in the previous class. What happens, how the different components of the electric and magnetic field exist across boundaries. We will make our life simple and say that no, the medium is infinite, there are no boundaries as of now. So for the sake of discussion, the fields could exist uniformly in all directions. Then we discuss something called as homogeneous medium. Homogeneous medium is defined as a perfect dielectric. A perfect dielectric or a perfect insulator where no static free charges, whether static or moving, they exist. The other assumption is that it should be isotropic. We have already discussed what is isotropic medium. It is the property of a medium that its quantities like permeability and permittivity are not direction dependent. They are single real quantities. So the second assumption is that what about the source or what about the cause that is producing these fields? That is either static charge or moving charge, or this current element which may be time varying in nature. So we can say that for the sake of simplicity in our discussion, the source or cause of the fields is far away. We are considering some part of the field of the medium where the effect of the source is felt but not the actual source. Now there will come a time when we shall discuss about how this current element is causing the magnetic field in more detail, and how by making this current element time varying we can actually make the fields also time varying. We shall look at this analysis in a little more rigorous manner as we move along the course. But for the time being, let us consider some part of the space or the homogeneous medium where this current element is really far away. We are not really concerned about where it is, as long as it is producing some field and we are concerned in this area, which is really, really far away from the current. So unbounded media is a very good approximation. Now, using these assumptions, we should try to look at what could be the solutions that may be possible from the Maxwell's equations. Well, it may be possible that there exists more than one solution, but in that case we shall look at what is the simplest of all solutions, because that's what we want, and we must believe the simplest solution, because even the best of solutions provided by nature are very simple. In fact, that is the assumption with which we shall go. So with this, let us write down the Maxwell's equations in unbounded medium. So since now the medium is unbounded, we can write the Maxwell's equations in their differential form. As we discussed, differential forms are easier to handle. So let's write the Gauss's law. This is Gauss's law for electric displacement. Then Gauss's law for magnetic flux density. Then comes Faraday's law of induction, which is nothing but this, and the modified Ampere's circuital law, which is nothing but this. Now, we have said that we will assume that our medium is a perfect dielectric, homogeneous. So in that case, we know that no free charges can exist and dielectric medium cannot have a conduction current because it is an insulator. So for a perfect insulator, rho and J are identically 0. So in that case, the Maxwell's equations essentially become something of this kind. So you may ask, how come the divergence of the electric displacement is 0? Remember what we said? We said that we are not concerned about the source. We are not concerned about the cause that is producing it. And we are standing in a point of observation that is far away from the charge. So let us say even if there is a charge which is producing some electric field or displacement. Suppose I am really far at a point where the field lines are so far away from the charge that they are almost parallel. So here I can definitely say that the divergence is 0. So now these are the Maxwell's equations which are sort of derived as a result of us being in the homogeneous dielectric medium. So now we know that the B vector is nothing but mu times H, and D vector is nothing but epsilon times E. So let us substitute these over here, and in the Faraday's law and Ampere's law, what we essentially get is this. And so as you can see that these are kind of differential equations which are coupled. We have a space differential of the electric field which is giving us a time differential of the magnetic field. And here we have a space differential of the magnetic field which is giving us a time differential of the electric field. So if you recall, when we were discussing about transmission lines, one of the very first results that we had got using the per unit length parameters of the line RLGC, we saw that we get a pair of coupled differential equations which have to be solved together. So therefore, the easiest way to do is to take another derivative of each. So what we can do, these essentially show that as a result of Maxwell's equations, that the E and H fields are dependent on each other. The moment one becomes 0, the other will also become 0. So they cannot coexist without each other. So what we can do now is we can take the curl of each and then see what happens. So if I now take the curl so this will be nothing but minus mu, the time differential of this, the curl of the magnetic field. Likewise, if I take the curl on the Ampere's law, I will get so we now know what this is. We know the right hand sides thanks to Ampere's law and Faraday's law. So we know that curl of H now is nothing but epsilon times the time differential of the electric field, and curl of E is nothing but related to the time differential of the magnetic field. So if I substitute, what I will get essentially is minus mu epsilon del square E by del T square, and here I will get minus mu epsilon del square H by del T square. This is what the right hand side would become. Now let us consider the first equation, the curl of E. Now this is slightly long to evaluate, so I shall give you the result directly, which you can prove using vector calculus very easily. The curl of any vector is nothing but the gradient of its divergence minus this. Now this del square is called the Laplacian operator. So this is nothing but this. This is the Laplacian operator. So we can expand the left hand side in this way. Likewise, I can say that this will become something very similar. But we already know that since we are in unbounded homogeneous medium, as per the Gauss's law, these two quantities would be 0. So therefore this and this would vanish. So what we see is that the left hand side would essentially reduce to this. So now I can rewrite and say that the second order space differential of E is nothing but the minus and minus will get cancelled out. So now we have been able to separate the E and H as two independent equations. Although we know that implicitly they are not independent, but at least looking at them variable wise, we can say that they are independent. Now, does this remind you of something? Does this remind you of something? Yes, these solutions are very, very similar to the voltage and current solutions from the transmission line. So if you recall, in case of transmission lines, we had something like this. So the left hand side is a space differential. The right hand side, well, we cannot call it a differential, but still there is this second order term which is there. Now we know that in case of transmission line, the solution for the voltage and current gave us a wave. So there is every reason to think that even the solutions for the E and H field from the Maxwell's equations, because of time varying source, will also give us a wave. So therefore, these two equations are the foundations behind what we call as the electromagnetic wave. Notice that once again that the nature of the E field and H field differentials is very similar to the voltage differentials and current differentials on the transmission line. So therefore we can definitely say that there is every chance that just like transmission line solution was a wave, even this will be a wave. The only thing that we now need to address is this time, which was not visible over here. We introduced time later in transmission lines. Although our analysis, what we had done for transmission lines was by freezing the time. But right now, since we are saying that let us assume that our sources or the cause which are causing the electric field and magnetic field are time varying, let us not do away with time. In fact, let us put the time variable. So in general, so as you know, the electric and magnetic field vectors are functions of the three-dimensional axis x, y and z, and because the cause that is producing these fields is time varying, as we have assumed, they will also be function of time. So therefore the electric field will be function of x, y, z and time, just like in transmission line the voltage was function of x and time also. The magnetic field will be functions of x, y, z and t, just like how current was a function of x and t also. Now, if we say that the current element that is producing the magnetic field and along with that the electric field because of the time varying magnetic field, if this is sinusoidal, that is of the form of e raised to j omega t, then I can definitely say that since the time and space variation are governed by different phenomena, in general the time varying nature of the electric and magnetic fields will also be sinusoidal. So therefore, just like how we had said in transmission line, it is Vx times e raised to j omega t, and this is I of x times e raised to j omega t. I can definitely say this electric field is nothing but the product of its positional vector times the time harmonic. Same for magnetic field. Now what you can see is we are slowly correlating what we learned in transmission lines with the result of the Maxwell's equations, or rather what form in general they can be. So now if I take the time derivative of the electric field, suppose I get something of this kind. So this will act like a constant because this is not a function of time, but this is a function of time. So it is like saying I will get something like that is nothing but the whole electric field vector. Now if I take the second differential with respect to time, what will happen is we will see minus, so j omega and j omega will get multiplied, so we will get omega square times E xyz times this. So we can say that taking a second order time derivative is equivalent to multiplying the whole electric field vector as a function of x, y and z with omega square, or rather minus omega square. So I can say that the second order time derivative is very similar to multiplying with a minus omega square. So let us now encode the time behavior using omega, and what we got for the solution of the Maxwell's equations, let us rewrite it. So what we had got was something of this kind. So now let us write this in the way we derived by replacing the second order time differential and for H field it is something of this kind. So these two are called as the wave equation. Notice how they are very similar to the voltage solution, which was V of x, or rather d square V by dx square, which is equal to gamma square V, and d square I by dx square equals gamma square I for transmission line. Now, in case of transmission line, let us assume that it is lossless, which means the small gamma is equal to nothing but j beta. So if I now put this, what will this become? It will become d square v by dx square is equal to, it will be j beta the whole square, so minus beta square v and d square I by dx square is nothing but minus beta square I. So what we are seeing is that the wave equation in nature is very similar to the transmission line, which is lossless, the solution for which is voltage and current, except that in space the solution is now E field and H field. So we know that current is related to magnetic field and electric field is related to the voltage or the potential. So therefore these are very analogous terms. So what you can see now is, by looking at the wave equation, it is not just the whole electric field which has to satisfy this equation, but it is the individual x, y and z components also which has to satisfy this. So it is like saying the Laplacian operator we have defined as nothing but this. I can also write that even one of these differentials must satisfy, because both left hand and right hand side are vectors. So therefore I can equate the x, y and z components individually. So it is like saying For example, let us take electric field. Just like how we have established this, I can also say that the x component will be equal to, likewise I can say for the y component also, well, in this case there is no need to write the vector notation because we are talking about the individual components, and so on. We can do for Ez the H components. Now what we have proved is that just like a transmission line, if the source or the cause of the wave is sinusoidal, the time dependency is also sinusoidal. So the field components of any electromagnetic wave, which are nothing but solutions for the wave equation, they exist in some kind of sinusoidal form. But now that was the easy part to understand. We have to now see what is the exact relationship between the field magnitudes, their directions, individual components. That is very important. Remember now that unlike transmission lines, we are now no longer working on one dimension. We are now in a three-dimensional space. What is important to know is that we have proved that even though we are in three-dimensional space, this solution or the nature of the solution of the E and H fields in any electromagnetic wave is identically very similar to the solution for voltage and current on transmission line. So even though now we have got a very solid motivation behind studying the nature of the waves, because we have correlated it with something that we already know. The next part is now not so simple, because unlike transmission line, the field components of the wave, they exist along all three axes. So we have to now see, as the next part of our analysis, how the components are correlated. So what we can see is, since the solution for the wave equation is some sinusoidal quantity, one way to look at the solution is to examine various kinds of forms, because now Ex, Ey, Ez, Hx, Hy, Hz, they may be their own individual sinusoidal nature, but how are they interrelated, the three xyz components, that remains to be seen. What we can check is, we can substitute some well-known forms for E and H in the wave equation and then see whether it works out or not. So in today's class, we looked at how we can use the Maxwell's equations to correlate the E and H fields in more closeness, assuming that it is the same cause which is producing them, that is a current element. But we are not looking at the current element per se, we are looking at a point in space, homogeneous medium, which is very, very far away from that space, and there we are analyzing the fields which are generated due to that current element. So in the next class, we shall proceed and examine what could be the solutions for the wave equation. Thank you.